All right. Okay, I think we're ready to go. Was there a markdown file for me, by the way? Thank you. Cool. All right. Okay, so let's go ahead and get started. So we started at the very end of last week talking about longitudinal models, specifically about growth models, right? So we did a little introduction to linear growth models. We didn't finish everything I wanted to say about that. So I want to finish the PowerPoint. I want to talk a little bit more about individual growth models conceptually. And then we're going to turn to pretty early on today, actually, we're going to turn to R, and we're going to run a series of growth models in R, linear growth models. And we're going to do models that sort of an unconditional linear growth model, and then we'll add a time invariant covariate. And then next week, we'll talk about time varying covariates. And then the third week, we'll talk about modeling piecewise and polynomial growth trajectories. So we've got sort of 3 weeks of growth modeling ahead of us. I know, these are probably my favorite 3 weeks too. And I think for a lot of you, maybe, I don't know, maybe a lot of this will start to come together during the longitudinal piece, because I think thinking about growth slopes as slopes somehow seems a little bit more intuitive to people than thinking about things like SES slopes as slopes. I mean, they are both slopes, right? Or gender slopes as slopes, but a growth slope as a slope is very intuitive. But then once it clicks and you go back to the organizational models, everything holds true. So I feel like the longitudinal models often sort of things start to click really well in terms of what we're doing and why we're doing it. I hope. So, okay. So, and I have some really fun examples too. I mean, I just think it's fun. Like, you thinking about how to model growth trajectories, I think is really, really fun. Okay, so we didn't talk about this last week. I think I skipped this slide last week, but this is going to be a really important topic of conversation today, which is when we remember last week, I said we have to have a variable that clocks the passage of time. So we need a time variable of some sort. And if you sort of think about modeling growth, if you were to just graph growth, forget about doing a multi-level model, right? You would have your outcome variable would be on the y-axis, and then time would be on the x-axis. So how do people change across time, right? So you need a variable that clocks the passage of time. And as I mentioned last week, it's really, really important for this variable to actually be equal interval, or something that you can assume to be equal interval, right? So that the difference, again, the difference between a 0 and a 1 and a 1 and a 2 and a 2 and a 3, those should be equal. Those should be equidistant. Because again, you're using time on the x-axis, right? So we need something that's, time needs to be in some sort of equal interval units. Okay, great, fine. But now we could have time structured data, or we could have time unstructured data. What does this mean? If we have data where everybody has the same data collection schedule, that's time structured data. So, and it doesn't necessarily mean that there are, and again, I need the variable to be an equal interval variable, but that doesn't mean that I have to be collecting at equal intervals, right? So I could have something where I collect data, let's say, from people at the start of the study, 3 months into the study, 6 months into the study, and then after a year. So I've got like 0, 3, 6, and 12, right? And I do that for everybody. So everybody's data collection schedule is like 0, 3, 6, 12. Okay, months are my unit, because like time could be in a lot of different units, right? It's really going to depend on your study. Your time units could be minutes, hours, weeks, days, weeks, months, years. Really not decades. That seems a little long, even for a longitudinal study. Years probably about as big a unit as you would probably want, but I guess it depends on biggest unit I've ever seen anybody use is years, but in some studies, if certain types of studies, they're using like milliseconds or something, right? I don't do that kind of data, that kind of research either, but, and we'll talk about using age. Age would be another way that you could kind of clock this time variable. But again, you get the idea that it would be like 0, 3, 6, 12, right? Months are equal intervals, so I checked that box, and everybody's data are collected at the start, after 3 months, after 6 months, and after 12 months. That's what I mean by time structured data. So everybody's data collection schedule is the same. That makes sense? Okay. So what's the alternative? Everybody could have their own data collection schedule. So let's say person 1, their data are collected at 0 months, 3, 6, and 12 months. But maybe person 2's data are collected at, the start of the study, and then 4 months, 8 months, 11 months, 15 months, right? Now I know how many months. I mean, I've clocked the passage of time for that person, so I know when their data are collected, but they don't have the same data collection schedule as the first person, right? And maybe the third person still has a different data collection schedule. Maybe I collected their data at 0, 2 months later, then 5 months, then 10 months, then 11 months, right? And so now with time unstructured data, everybody can have a different data collection schedule. Yes. Yeah, that's a really good question. So the question was, do you need to have the same number of data collection points? So whether we have time structured data or time unstructured data, we can deal with missingness in the sense that, like, somebody's just missing a data point, right? That's okay with either time structured or time unstructured data. But yeah, I mean, you don't, especially with time unstructured data, I guess you don't even really necessarily have to be aiming to have the same number of data collection points for every person if you didn't want to. Although, I mean, like generally you're going to aim, I'll just say, it's a good idea to aim for the same number of data collection points for every person to start off with. But if people don't show up or they end up with different numbers of data collection points, that's okay. That's fine. And actually that'll be okay whether we have time structured data or time unstructured data. The big difference is if it's time structured data, I mean, you kind of need to know which point is missing, right? Are they missing at 3 months, or are they missing at 6 months, or whatever? So, I mean, you might be thinking to yourself, why would I ever want to use time unstructured data? It seems like if I'm designing a study, wouldn't I want to know I'm going to collect data for people, like I'm going to start at the beginning, and then my next follow-up is going to be 3 months out, and then 6 months out, and then 9 months out, or whatever, 0, 3, 6, 12. So why might you end up with time unstructured data? Yeah, yeah, okay, so that's a good point. If it's event related, it might not be on a particular schedule. Good point. Yeah. Yeah, that's exactly right. Sometimes people can't stick to the structure that you have specified. So I would say that the vast majority of the time, even when we start out designing a study where we think we're going to have time structured data, it's pretty common that it ends up becoming somewhat unstructured, right? Like the best laid plan. So you say, I want everybody to come back for this follow-up visit to the lab 3 months after their first visit. Well, some people might make it like 3 months later. Some people might not get there for 4 or 5 months, right? And let's say you have trouble getting this person back into the lab and they don't come for 5 months instead of 3 months. Well, should that be the 3-month time point? Should that be the 6-month time point? And they're missing the 3-month time point? Yes, Claudia. When you say sickness for different people, do you mean you're starting at the point at which they get sick? Yeah. Well, so then you also have to think about where the start point is. So it's not necessarily that just because people get stick at different points that they have to, I mean, you may end up, I don't know, you may end up with time unstructured data. But for example, if people come into the study when they're diagnosed with cancer, let's just say, so they get their diagnosis and they come into the study, then you want to think about how you're going to center your time variable. And usually you would center it so that they, maybe you center it at the time of diagnosis, for example. So 0 is the time of diagnosis for the person. So it is true in that case that each person's time of diagnosis is, like, if you looked at a calendar, going to be a very different calendar date, but 0 still means this is the moment at which you became diagnosed. Does that make sense? Okay. Yes. That's true. That's true. That's true. Absolutely. So formative assessments are often time unstructured data. So there are lots of reasons we might want to collect time unstructured data. It might make, or the data that we're collecting are time unstructured. But again, I would say, even when you think you're collecting time structured data, or you want to be collecting time structured data, it's pretty common to end up with something that looks at least a little bit time unstructured. Okay. So I would say one of the big advantages of using multi-level modeling to fit growth models as compared to structural equation modeling is that it's really like natural, intuitive, super easy to use time unstructured data in a multi-level model. And the reason for that is because time is actually going to be an independent variable in our model. So we're going to have a variable that clocks the passage of time. And because it's a variable, right? So imagine it's a column in our data file, right? It's a variable. That means that each person can have their own individual values for time. And because each person can have their own individual values for that time variable, I mean, that is what time unstructured data is, right? That each person has their own time values. So because in multi-level modeling, time is actually a variable in the model, it's really, really easy to accommodate time unstructured data. So again, for those of you who took SEM, just to kind of compare that to what we did last semester, in SEM, when we fit growth curve models, remember we had a latent variable for the slope and we had a latent variable for the intercept, right? And the latent slope variable, the loadings, were actually what contained the information about time. But if you think about the loadings containing the information for time, then you remember that we only have one set of loadings actually across the entire sample, right? So that's why sort of the natural, again, there are ways in M+, and I think I briefly mentioned them last semester, but there are ways in M+ to deal with time unstructured data in an SEM framework. But the actual, like, traditional SEM framework for growth curve modeling doesn't actually handle time unstructured data sort of organically, because all of the information about time is in the loadings, and we only have one set of loadings across the entire sample. So this is a place where I give the, for keeping track between, like, SEM and multi-level in terms of how I want to do my growth modeling, this is a place where I'm going to give a big, like, check mark for multi-level, big advantage multi-level for if you've got time unstructured data. And because it's so easy, because everybody can have their own, because it is a variable and everybody can have their own time schedule, again, even if you think it's time structured, but somebody show, you don't even have to think about it really that much. Like, a few people come into the lab a little bit late, that's fine. You just keep track of the time, that, just keep track of their information, put it in that variable, and off you go. So it could be like 80% of the people look time structured and 20% are off a little. That's fine. It doesn't, right? It doesn't have to be, like, in some sense, an either or. Just time is going to be in this independent variable, so we can handle time structured data or time unstructured data really, really easily. Okay. So we can handle any kind of data structure in terms of our time variable. And, because we have time unstructured data and because we, just sort of the nature of what we're doing, we can totally deal with people who have different numbers of data points. I mean, it's not just because of the time unstructured nature of the data, but because that's true in SEM too. We can handle people who have different numbers of data points. So missing data at the observation level is not that big a problem. So that's what I mean by individual growth modeling doesn't require balanced data. So you all are young enough that you probably never had to do anything in repeated measures ANOVA, but back in the last century when people used repeated measures ANOVA to look at change across time, well, no, it's true. And if you were to actually do something in repeated measures ANOVA, the real problem with it is if you run, because you can fit things that look kind of like growth models and repeated measures ANOVA. But the problem is that you have to have balanced data. You have to have the same number of data points for every person. And so like if you have 4 data points and somebody only shows up 3 times, unless you do something fancy like multiple imputation or whatever, they get kicked out of your data file. And of course, anybody who's done a longitudinal study knows that like, if you run a longitudinal study for long enough, the majority of people might end up missing 1 data point, right? And so you can't be listwise deleting people every time they miss they miss an observation, or you could go from a data set of like 200 to a data set of like 50, right? And that, for obvious so obviously you were going to use a repeated measures ANOVA, you would have to deal with your missing data in some better way because you can't listwise delete, 3/4 of the people and say anything about it. But the good news is here, we're going to use all of the available data. So if somebody has, if I've collected data across 4 time points and somebody only has 3 of those time points, we're going to use those 3 observations across the 3 time points. If somebody only has 1 time point, we don't ever have to delete people from the data file. We're going to use all of the available information. Now, if somebody only has 1 time point, can we actually estimate a slope for that person? What do you think? No, obviously not, right? So, but again, we don't have to do any kind of deletion or worry about that. We're going to take all of the data that we have and use all of the data. Okay, so basically every person's sort of growth record, so that's like our, we're keeping track of their time, right, and their change across time, can have a unique number of waves collected at a unique, at unique occasions of measurement. No problem, which is great. That's really flexible. Okay, so just remember, we started to talk about this last time, but yes. Oh yeah, sorry. Would I ever use time if I'm, I don't, can you say a little more about what you mean?
In this way.
Yeah, so you can, if you have 3 time points and you've sort of got, let's say time 1, time 2 is like where the mediator is and time 3 is the distal outcome. I wouldn't fit a growth model to that. I would still have that as like a mediational model. So whatever's happening at time 1, then I've got this mediator thing at time 2, and then this outcome thing at time 3. But you could theoretically, not in that case, you'd need more stuff going on, but you could theoretically have models that combine growth and mediation, right? Yeah, but I'm not gonna do that today. But no, if you just had 3 time points and you had like a mediation model, I wouldn't reframe it as a growth model, because that's, really, again, really different assumptions about what you think the process is that's generating that data. So it's always about how do you, what's your model for the data? How do you think this is sort of occurring? Okay. So multi-level model for change. So we talked about this really briefly at the end of class, but here when we reframe our multi-level models as longitudinal growth models, level 1 here is really about within person change. So we're thinking about within person. Observations are within person, and people are actually our clusters here. So like our cluster variable is going to be our person ID, and we have observations across time, which are nested within people, which makes sense, right? And obviously there's going to be a huge amount of dependence within person. And in fact, more, if you think about it, generally speaking, there's more dependence across observations within person than there is across people within a school. That kind of makes sense to you, right? Like people's own observation, like it's one person and I collect these data points across time, they're going to be more, like there's going to be, I would expect to see like a higher within person correlation than I would expect to see like correlation of people within a school, right? So it's pretty, I mean, again, I don't know. I don't find ICCs to be as useful in the longitudinal context personally. They're always really high, of course, right? We can compute an interclass correlation coefficient in a longitudinal context just the same way we would do it in an organizational context. So we would just take the between person variance divided by the total variance. But again, usually when you do that, you're going to find that the ICCs are like 0.5 or above. They're going to be huge because a lot of the variability is going to be, well, I don't know. Again, I shouldn't say that because it really depends on your model and your design and all kind and the amount of time and that kind of thing. But they're definitely going to be bigger than they are for organizational models, substantially bigger. Okay. So as we said, multiple observations are nested within people. We need at least three time points for longitudinal models. We talked about that last time. If I want to model just a straight line trajectory, 3 is my minimum. If I want to do a fancier trajectory, something nonlinear, which again we'll talk about in a couple of weeks, then I would need more than 3 time points, and we'll talk about how many more when we get there. Okay, and remember, do you all remember how you freaked out last week when you saw this slide? But you feel better now, right? Because I allayed your fears that we are changing our notation a little bit here, but it makes sense because now notice that our betas, we're still using betas at like level 1, right? Or sorry, at the person level. So not at level 1. We're still using betas at the person level, but the person level here is level 2. So the person level in an organizational model is level 1. The person level in a longitudinal model is level 2. So instead of using betas at level 1, now we're going to use pi's at level 1. And this is the Rodenbush and Breich notation. Again, if you go to different books will use different notation for multi-level models, but I happen to like the Rodenbush and Breich notation, so I'm gonna stick with that. So when we think about within person change, we have a person's outcome score, that's the Y. And now we've got, instead of IJ, I've got TI. Why? No pun intended with the Y. Why? Because T is observations across time nested within person. So the T is for time and the I is for individual, right? So we've got an outcome score for person I at time T, and that's going to be a function of this pi sub naught I is the randomly varying intercept for person I, right? So each person has their own randomly varying intercept. And then pi sub 1i, that's going to be the randomly varying growth slopes, right? So this is the linear growth slope for person I. And the independent variable here is time. And again, you see the TI there. That means I'm measuring time. I'm going to have a variable that's going to be my time variable in the data file. And I'm going to have a measure for time for each person. I'm going to have a measure of time at time T for person I. So like this is, and if you think about this, this is exactly why every person can have their own unique sort of data collection schedule, because time is entering as a variable in the model. And again, we're going to talk about centering in a minute. We really have to think about, how do I want to center that time variable? Because the way that I center that time variable is then going to influence how I interpret the intercept, right? It's a linear growth model, so we're making the assumption that the rate of change is constant across time. And because the rate of change is constant across time here, the way that I center the time variable is not going to influence the slope, but it is going to influence the intercept in a linear growth model. And then the last piece we have is the E sub TI. So this is just the residual, right? This is the this is the difference between the predicted value of y at time t for person I and their actual value. And remember last week, let's see, can I draw on the PowerPoint? So imagine this is the person's trajectory. So, right, the intercept is going to be okay. But then, so we'll have like the predicted value at time 0, right? We're going to have the slope for the first line, and then these E sub TIs. That's really about the error in measurement at each of those time points. We have an error for each time point for each person. So it's really about I've got this predicted trajectory. How much error is there? How far off that prediction am I for each person? And again, remember that we're going to get, you can imagine there's an error for each person at each time point. And when we take the variance of those E sub TIs, that's actually going to be sigma squared. So sigma squared is our pooled within person residual. Just like in an organizational model, sigma squared was our pooled within cluster residual. But now remember, the cluster is a person. So now sigma squared is our pooled within person residual, right? So sort of imagine across all people, I'm kind of looking at how far off each person's observations at each time point are from their, sort of predicted trajectory. And I pool that across all people. And that's really going to be what my sigma squared is. So it's this measure of within person error variance, right? How far off people are from their predicted growth trajectories. Yes.
Is that a retail?
Yeah, when I say pooled, I mean pooled across all time points and across all people, right? And again, the actual computation of these things is not as simple as it is in OLS regression, but it is pooled across time points and pooled across people. So it is the pool within person residual. We're using maximum likelihood estimation. It's not an OLS regression. I'm not going to say it's the sum. I'm going to say it's pooled, right? Okay. So nothing is as easy as it was in OLS regression. So just kind of have to be okay with that. So this is our sigma squared. Now, in terms of between person differences or between person model, come back over here. So right now, by the way, this is what I would call an unconditional linear growth model. So it's unconditional because I don't have any person level predictors right now. So what I'm saying though is that my intercept randomly varies, right? And the intercept is a function of beta naught naught, which would be analogous to gamma naught naught. And notice, naught naught, no letter in the subscript, right? So I'm getting one predicted or expected, like overall intercept, the intercept, which is what? The predicted score, right? The sort of overall predicted score when time is equal to 0. So we really have to think about, again, come back to this in a second, but we really have to think about then, how do I want to center time to make that make sense? My overall intercept, right? My expected intercept, which is going to be the predicted when time is equal to 0. And what's my R sub naught J then? This is, again, it's capturing it's the capturing the between person differences in the intercepts, right? So each person, we have like an overall intercept, and each person has their own intercept. And this is really capturing, the residual is capturing the difference between a person's intercept and the overall expected intercept. Right? So that not everybody's we're gonna get an overall estimate for the intercept across the entire sample. What's the average intercept, or what's the sort of model predicted intercept? But people are gonna deviate. Not everybody's gonna have the same intercept, right? So the difference between the model predicted intercept and person I's intercept, that's really what's being captured in this R sub naught J. Does that make sense? And the same thing is going to be true for the slope. So I've got each person has their own slope trajectory, right? So I could have, again, let's imagine I've got something that looks like this, say the intercept is there or something, right? You can see everybody's got different intercepts, everybody's got different slopes, right? So we've got some overall estimate of the slope is going to be my beta 1 naught. That gives me my overall expected linear growth slope. But this R sub 1j is giving me the residual. It's really the difference between person I's slope and the overall model predicted slope. Right? That makes sense? And again, yes, let me do this. So these are not actually parameters in my model, but the variances are. So the variance of R sub naught I is going to be tau naught naught. The variance of C, the variance of R sub 1 I is going to be tau 1 1. And again, just like we did with the organizational models, we're going to generally default to fitting an unstructured matrix, which means that my tau matrix is going to estimate the variances on the diagonal, and I'm going to estimate the covariance between the slopes and the randomly varying slopes and the intercepts on the off diagonal. So this tells me about how much between person variance is there in the intercept. Again, know how I centered it to really interpret it more than that. This is the between person variance in the slope. And this tau sub naught 1 is the between person variance, or covariance, sorry, the between person covariance between the slope and the intercept. So is there a relationship in this case between the intercept and the growth slope? And again, in longitudinal models, that's often something that we're very interested in being able to interpret. We want to know, let's just say that I centered the intercept so that the intercept is where people start, and then the slope is how fast people grow. So that this covariance would tell me, is there a relationship between where people start and how fast they grow? Which obviously is something that we'd be really, really interested in. Yes. The tau naught 1. The tau naught 1. So we've got a tau naught naught. This is the between person variance in the intercept, between person variance in the slope. And then we're always, again, less, we're always going to basically want to be fitting an unstructured tau matrix unless you're told to do otherwise, or unless you've got a compelling reason to do otherwise. And so in that case, that means we're estimating not just tau naught naught and tau 1 1, but we're also estimating the covariance between the randomly varying intercepts and the randomly varying slopes. And that's tau naught 1. And so that tells me about the relationship between the slopes and the intercepts. So far, so good?
So this is generalized to no matter the number of times.
Yes, it would not right here. I could do this with 3 time points. I could do this with 10 time points. I could do this with 20 time points. It doesn't matter, right?
I guess what always confused me, not having a predictor. Just looking at the change, score, time, and
Yeah, exactly. We've got only one. If you think about it this way, we've got one predictor, and it's a within-person predictor, and that predictor is time. So this model is really saying, how well can we predict scores using time, right? And that's it. That's exactly right. We don't have any between-person predictors yet, but this is a really helpful baseline model because obviously I can see if there's any kind of linear growth slope, but then I can also look, let's assume that a linear slope is a good slope for whatever I'm doing. Then I can also say, well, okay, so on average, people start here and they grow by this much, but yeah, how much between person variability is there in terms of where people start? And how much between person variability is there in terms of how fast they grow? And if there is a lot of between person variability in terms of intercepts and slopes, then the next question we're going to ask ourselves is, do I have any, they could be within person predictors too, but for this week, we're only going to be thinking about between person predictors. So do I have any person level predictors that might help to explain why people differ in terms of where they start and or how fast they grow? And just like we said in organizational models, you could have different predictors to predict people's intercepts as compared to people's growth slopes, right? So you could think that maybe something up, like maybe, whether let's say we're looking at reading growth from the start of school through 2nd grade or something, and you might think that, whether they attended a preschool program or not might help to predict their reading start values at the beginning of school, but maybe you don't think that that's going to predict how fast their reading growth actually, maybe you don't think that'll predict growth starting in kindergarten. Maybe you think again, you could think that. Again, you need to think about what your hypothesis is, but maybe you think the big advantage of preschool is it helps you come in at a certain level, but you don't actually think that it's going to influence the growth rate once you're in. It's just that kids who've had preschool, they come in at a higher level than kids who've not had preschool, but I kind of expect everybody to grow at the same rate, right? That would say, okay, I should put preschool in. Do that. Have the random effect. I could have something else. I could say, okay, then I think preschool attendance is gonna. There we go. So I could say I think preschool attendance is gonna predict, where people start, but I don't actually think preschool attendance is gonna predict kids' growth rates from kindergarten to 2nd grade. Maybe I have a different variable I think is gonna predict kids' reading growth. I don't know what it is, but there could be something else, right? Or your next door neighbor in your lab could be like, no, that's wrong. I actually think that if you go to preschool, it's not just going to influence where you start, but I actually think kids who go to preschool are also going to grow faster from kindergarten to 2nd grade. Well, that can then become an empirical question, right? Does preschool actually moderate the growth rate from kindergarten to 2nd grade? Sense? But right now, this is again what I would call an unconditional linear growth model, and this is generally where we want to start. You could start with a model. If you really want to. I don't know that I make you do homework, but you could start with a model. It does not include time at all, and that would be a completely unconditional model. So then you would, right? And then you could actually, all you'll really get there is, well, what is the intercept here? This is actually a good thought experiment. Let's say we do this. So now I don't have time in the model at all. What is the intercept? yeah, if you think about it, right, I don't have time in the model anymore. So it's like, each person, if you think about it, each person has their own like app. So let's go back here. Let me draw my little points. So let's say this is person one, but I don't have a linear slope anymore. So what would I be doing? I'd be basically drawing a flat line for person one. And let's say I've got person two, and now I'm drawing like a flat line for person two, right? And so if you think about it, then really each person basically has their own individual average across time. That's really what this pi sub naught I would be. And then this beta naught naught would be like the average of these averages, right? So I've got, these are like the person averages. And now I've got like the average of averages. And so this beta naught naught would be like the expected average across time and across people, right? So, but I'm not allowing for growth there at all. I mean, again, if you don't have growth, actually, this might be a very reasonable model. I mean, you can have longitudinal data where you don't actually expect to see any growth. So a classic example of the kind of place where a model like this might actually, it wouldn't be a model that's this simple. You would put some covariates in it, obviously, because this model is pretty boring. But a place where a model like this actually gets used, it's not uncommon to use models that are kind of like this with intensive longitudinal data. Because you might not actually think that, for example, let's say I'm looking at the relationship between mood and stress. So like mood is my outcome variable and like daily stress level is my independent variable. And again, I know I don't have an independent variable in here yet. So I'm just talking about this conceptually. I don't have it in the model yet. But like I might think like how stressed you are influences your mood. But do I actually think that people's moods are going to like systematically get better or worse across time? No, I probably think that people have a homeostasis in terms of their mood. Like I do think some people tend to be in better moods than other people. So I do think there's going to be variability across people in terms of what their average mood level is. But I don't necessarily think that like if I collect mood data across an entire month, that I'm going to see that like people their moods systematically get better or worse. I mean, again, maybe you do, then you would want a slope. But I would say, in general, we don't think of mood as being something that's really like growing across time, but it is influenced by all kinds of things that are happening on a day-to-day basis, right? So if that were my model, if I were looking at sort of an intensive longitudinal study and I'm going to look at the relationship between mood and stress, then this would actually be a very logical unconditional model to start with, where I'm just saying everybody's got their own sort of homeostatic mood level. And now this is going to tell me about the within person variance, right? Like how much variability is there within people from their own sort of like means, right? And this is going to tell me about the between person variance in that sort of homeostatic like mean level of mood, right? And then I could start to add predictors to try to predict. But so it might seem like a really dumb model, but there are times when actually this is a good starting model. But again, remember I said last week, we're going to assume we're looking at growth. We have models where we think there's going to be growth, so we want to track the passage of time. Yeah.
So would this also be helpful? What if you have like a amniotic like cortisol, for instance, right? It has this peak and then it drops off and has this decrease, right?
So you're saying, what if you had something that looked like this, maybe?
Right. Throughout the day, you could have like a stressor predicting that spike. And
so, I mean, that's a perfect example of where we're going to want a nonlinear growth model. Like we wouldn't want a model that doesn't have growth at all, because, right, then if, with this model, you would just, well, okay, I take that, unless you really think that whatever your independent variable is that you're getting can really track this trajectory, which maybe it can, but if you don't think it's going to really be able to capture that trajectory, then you're going to want to think about, you're going to want to think about what shape of trajectory you're looking for, and then also put in time varying predictors. So it really depends. And for some of those things, we're going to talk about polynomial models and piecewise models, but for some of those, like cortisol and things like that, sometimes they use different models like exponential models. So there are other nonlinear growth models that I'll briefly reference when we get to the nonlinear part. But anyway, so so that's going to be even more complicated. So we'll get there. All right, does this all make sense to everybody? And then we're going to combine and just text. That's annoying. Maybe when I click out of it. So now I can combine, right? And what I'm going to do is I'm going to substitute in this beta naught plus r sub ij is going to get substituted in for the pi naught sub I, right? And the beta 1 naught plus r sub ij is going to get substituted in for the pi 1 sub I. And once I make those substitutions, then you can see I've gotten rid of my pi. I'm going to have beta naught. Here's the r sub naught I, right? Plus beta 1 naught times time sub ti plus r sub 1I times time sub ti, right? When you do that substitution, that's what you get. And then finally, you can't see it because it's under there, but we still have our e sub ti, which is our within person residual. So this would be my combined model that I would be fitting. Is everybody clear on kind of how these equations work? Does this make sense? Yeah? Okay. All right. So I think I've said all of this already. Right, so I've just got the level 1. Here's our level 1 equation. Just to kind of reiterate that our intercept is really going to be our expected value when time is equal to 0. So we're going to have to spend a lot of time thinking about when time is equal to 0 and what makes sense. And then it's pretty common to assume that the E sub TIs are normally distributed with and we did this with our R sub IJs too. We're going to assume those are normally distributed with a mean of 0 and a constant variance. There are ways to model that if you don't want to make that assumption, but for right now, let's just stay with that assumption. And I would say it's especially important when you're in longitudinal models that before you move on and start modeling like a full model with level 1 and level 2 predictors, it's really important to start by building the level 1 model and making sure that you have a good model that can describe people's individual growth trajectories. And you can really look at that within person variance. So the goal of the level 1 analysis is really to describe the shape of each person's individual growth trajectory. And generally speaking, and again, there are exceptions to every rule, but generally speaking, when I build longitudinal growth models, I like to start with an unconditional model, and I really think about the shape of the growth trajectory first. So is it linear? Is it nonlinear, right? So is it linear? Is it piecewise? Is it polynomial? Whatever. So I really try to model the shape of the growth trajectory first. And then the next thing I do is I add my level 1 covariates, which are my within person predictors. And I get my full level 1 model set. And it's not until after I have sort of the level 1 model the way that I like it that I start to add level 2 predictors, which are, again, the moderators of those level 1 growth parameters. And I do have an example, I think I'll show you next week, where, because if you have the wrong shape for the growth trajectory and you put in level 2 variables as predictors of those growth trajectories, but if like the trajectory itself is misspecified, then you can make some major inferential errors in terms of what you say about the effects of the level 2, right? So like if I say, for example, I think the trajectory is linear when it's really curvilinear, and then I put in predictors of that linear trajectory, I'm not necessarily going to get the same results as if I actually correctly model the curvilinear trajectory and then look at what predicts the curvilinear trajectory. So I think in this case, especially, it's really important to be thinking about, let's get our level 1 model set. Let's make sure we're good with the level 1 model before we start adding level 2 predictors. So we'll follow that logic when we do stuff in class too. Yeah. Mm-hmm. Well, let's go back to, hold on. Erase this. So again, let's just stay with our simple model for this week. Complicated next week, right? But if I were to put in level 2 variables, the level 2 if I were to put in level 2 variables, I could put in a level 2 predictor that predicts the randomly varying intercepts, or I could put in a level 2 predictor that predicts the randomly varying slopes, or I could put it in as a predictor of both the randomly varying intercepts and the randomly varying slopes, right? So level 2, when you say covariates, I'm like not exactly sure what you mean, because we have covariates at like we have covariates at level 1 and covariates at level 2 potentially. Were you talking level?
So you said like
Oh yeah. So
those would not be random.
they
Yeah.
could be. They could be. Yeah, absolutely could be. So we haven't talked about that yet, but yes, they could. That gets fun. And that's another reason why you would want to really sort of get that whole level 1 model all settled and feel good about it before you start putting in your level 2 covariate. So yeah, I could have, for example, I've got time here, but let's say, well, let's just go with my example. Let's say it's not mood, something that would grow, but might also be affected by stress. I don't know. Doesn't that mean what? Weight. Okay, sure. So weight, let's say, is my y variable, and I've got time, so I'm looking at how weight changes across the passage of time. And then let's say that my x variable, I've got also stress, right? And so I'm measuring, but I'm not just asking people. So and this is another interesting thing, right? Like, is a variable a level 1 variable or a level 2 variable? Is going to depend on a couple of things. It's going to depend on how frequently you're asking somebody, right? And whether it actually varies within person. So for example, if I ask people about their stress only once at the beginning of the study, then I'm going to have to use stress as a level 2 variable. If I want to use if I want a level 1 variable, a time varying covariate, I need to ask it on the same data collection schedule that I'm actually collecting the dependent variable. Right? Or you could do something with like lag 1 or something if you wanted, but basically you're going to just think of it as like, if I want something to be a time varying covariate, I'm going to have to collect information on that across time. So like if I want stress to be a time varying covariate here, every time I collect people's weight, I'm going to ask them, hey, how stressed are you? Right? And that's good. That works out really well. So now imagine I've got that. So now I've got pi 2 sub I times stress plus e to ti, right? Now, jumping ahead a little bit here, but now I bring this down here and I say pi 2 sub I. What is pi 2 sub I? It's the effect of stress on your weight, right? It's the stress weight slope. So it's the effect of stress on your weight. So pi 2 sub I equals beta 2 naught plus, if I'm going to make it randomly varying, plus R2 sub I. if I allow that to randomly vary, what am I saying? Think about this conceptually. I'm saying that stress has a different impact on weight for different people. So like the relation, which makes a lot of sense, the relationship between stress and weight, it differs across people. So like maybe some people stress doesn't, maybe for some people stress doesn't influence their weight at all, like, right?
Exercise.
Right? Yeah. For some people, maybe stress actually makes them lose weight. And for other people, stress makes them gain weight, right? And I think that's probably actually very true. So this is a good example of a time varying covariate that would probably vary across people. And so now I've got R sub 2I, which is saying, okay, that's like I'm saying, right? That I'm saying that yeah, I'm gonna, this is the average effect of weight on stress. But having this R sub 2I is allowing for that to vary across people. So maybe the average effect, and this is actually a really good example too, because sometimes you can find that the average effect of something might be 0, but it still randomly varies across people. So maybe we might find in this example, the average effect of stress on weight is 0, right? So maybe my beta 2 naught is not actually statistically significant. The fixed effect is not statistically significant, but maybe there's tons of variability around that fixed effect of 0 because some people don't gain or lose weight when they're stressed. More stressed, like more stress doesn't affect weight. Some people, more stress, they gain weight. Some people, more stress, they lose weight, right? And so then that's really interesting, right? Do you kind of all follow me? And then as long as we've gone down this path, what does this do to my tau matrix? Ready? Hold on. Okay. Unstructured. I want an unstructured tau matrix. I've got 3 R's, so I'm going to have my 3 taus, right? I've got randomly varying intercept. This is the variance in it. So, right, I've got between person variance in terms of where they start off for their weight. I've got between person variance in terms of whether their growth, their systematic growth in weight. But hold on, we won't go too far down this path. It's going to be when the time varying covariate is at 0. So when I interpret this as my growth slope is going to be the growth slope when the time varying covariate is at 0. So I'm going to have to think about how I center the time varying covariate as well, right? In terms of interpretation.
Stress. So when stress is.
Yeah, so stress, when stress is 0. So this is going to be like, what's the predicted growth trajectory when stress is 0, right, across time? This is going to be the predicted effect, this is going to be the predicted effect of stress on weight. And then this is going to be the between person variability in that relationship between stress and weight, right? But it's unstructured. So now I'm going to have 3 more components of my tau matrix. This is still, well, not still, it's a little different. It's still the relationship between the slope and the intercept, but now it's really the relationship between the intercept and the growth slope when the time varying covariate is 0. So when stress is 0, right? This is going to be the relationship between the time varying covariate slope. And this is where people sometimes get tripped up. And again, we'll come back to this later, but this is going to be the relationship between the slope of the time varying covariate on weight. So the effect, so basically this is the relationship between weight and stress and weight, the relationship between stress and weight and where people start out in terms of their weight. And then this is going to be the relationship between the time slope, so the effective time on weight when the time varying covariate is 0, when stress is 0, and the effective stress on weight. And again, these get a little bit funkier. So like this, do I care about those two effects? Like, do I care about those two taus? I don't know. Maybe I do, maybe I don't. Sometimes they're more, when you do this substantively, sometimes you do it and you're like, wow, I don't really care about that. I never would have even thought about that, right? But like, that's what they are. But sometimes they really do make sense, you know? So, because maybe the growth slope, you know, how much people are growing, holding stress constant at some value is really, like that weight growth is related also to the way that they handle the way that stress then impacts weight in their body. You could imagine, I mean, like that's not a crazy idea, really. Okay, so we've gone down that rabbit hole. Is everybody cool? Yeah? Come back to time varying. We're going to talk a lot about time varying covariates next week. So we'll come back to this idea. But again, my point is we want to build our level 1 model, and we want to be feeling good about our level 1 model before we put in our level 2 variables. Having said that, today we're going to go with like a straightforward linear growth model and add in level 2 covariates. Yeah. Mm-hmm. Yeah, so yeah, exactly. It would look just like this. So you have I times stress, right? And then here we had, so now we're just gonna multiply through. And so just like we had an R two naught plus R2I. So just like here we had R so 1I times time TI, we would also end up with an R2I, right, times stress TI, right? And we'd also end up with the 2 naught times stress TI. So yeah, but again, we'll come back to this next week. We're going to talk a lot more about time varying covariates next week. Good? Okay. So, yeah. So again, the goal of the level 1 analysis is really to describe the shape of each person's individual growth trajectory. And after that, once we get to sort of thinking about our level 2 predictors, then we're really saying like, okay, there are differences in terms of people's intercepts and slopes, right? So we want to see, are there person level predictors that could actually help to predict the variability, the between person variability in slopes and intercepts? So, the taus, those variances are telling us about how much between person variability there is in terms of, again, let's say if we centered on initial value in terms of where people start and how fast they grow. And then the question is, can we find some covariates at level 2? Can we find some person level predictors that might help to explain why people start at different places and why people grow at different rates, right? And so in the level 2 model, we'd be looking for variables that are person level predictors that explain why people, why people start in different places and why they grow at different rates. Yeah. And as I said before, remember, it's not always totally obvious whether something is a between person predictor or within person predictor. There are certain things that are obviously only going to be between person, because there are things you can only measure maybe once per person. But there are other things that, depending on the design of the study, they could be within person. Like I said, that's how we started with stress, right? Like it could be a within person predictor, or it could be a between person predictor. If I only measure it once at the start of the study, it's going to have to be a between person predictor. If I measure it at every time point, it could be a within person predictor. But there's one other little hitch that I'll just mention. Just because you measure something at every time point doesn't actually mean that it varies within person. So like a good example of this is, I've done a lot of analyses with like the ECLSK data, which is this early childhood longitudinal study data that the federal government collected, and there's an SES variable in there, and they collected it at every time point. So it's like the family's socioeconomic status, and it's collected at every time point. But sadly, there, you know, and again, this is like multiple time points across just let's say a couple year period. So maybe it's like 4 or 5 time points across just 2 years of a kid's life. How much do you think family SES varies across a 2-year period? Like if you had a 20-year period, no doubt you'd see a lot more variance, I think. But like if you're just looking over like, let's say 1 or 2 year time span, yeah, I'm not saying it's going to be like absolutely identical across time for every family, but there isn't a ton of change across time. Like, so the families that were really low SES when the kids started kindergarten, they also tend to be really low SES families at the end of first grade, right? And the families that were really high SES at the beginning of kindergarten tend to be high SES families at the end of first grade. So even though it's measured, it looks like a time varying covariate because it's measured across time, there isn't actually a lot of within-person variability. Well, just like, I mean, any variable, we need variability for something to be a good variable, right? So if you don't find a lot of within-person variability on a variable, it's not a good within-person variable. So if you have a variable like that, even though theoretically you have 5 time points for SES, let's say, it's not a good within-person variable. You would still want to then put it at the between-person level, yes. Mm-hmm. Oh, yeah. So you can have, I mean, this is where things kind of get interesting. And this technically kind of becomes more of a cross-classified model than a strictly hierarchical model. But yes, you could have something that is, I mean, maybe, but you could have something that is across time that is not necessarily like, it varies across time, but maybe it doesn't actually vary, it doesn't vary across like people across time. So there are a couple different ways you can handle that, because if it really varies across time, but it doesn't vary across people, actually probably the simplest way to handle that is to put it in at level 1, but not allow for a random effect. So you're putting it in as a fixed effect at level 1. So you see what I'm saying? So you're allowing it to vary across time, but you're not actually allowing the effect of that variable to vary across people. Yeah, so like you're allowing it to vary across time and you're allowing, right? So
Everybody shifts.
well, I'm saying you could put it, well, you could put, I mean, again, you really have to think about what you're doing, what makes sense to you, but you could theoretically put it in at level 1 so that the effect, so like so let's say as inflation increases, that's having an effect on each person's predicted Y score, but I'm not allowing that to vary across people. You could, I mean, theoretically, if you have a good reason, you could allow for a random effect. Maybe you think, no, like the effect of inflation is going to vary across people. But maybe you think like the effect of inflation is going to vary across people as a function of their SES. So then you could put in an interaction between SES and inflation, right? Yeah. Yeah. Well, unemployment would vary. So actually, we have an example next week or the week after that's unemployment, where unemployment is a within-person variable. So people are like unemployed and then they become re-employed and then maybe they become unemployed again. So like if you're actually looking at people's employment status, that would be a within-person variable. And a within-person variable doesn't have to be continuous. It could be dichotomous. It could be something like unemployment status or whether or not you graduated or, right? Yeah. Well, I mean, wages is complicated because, like, yeah, if you're unemployed, you probably don't have any wages, right? But yes. Yeah. So anyway, so I guess the point of all this is you can do a lot of different things. You definitely need to know what you're trying to do, but there's a lot of flexibility in here. So there's not necessarily like a right answer, even with the same set of variables. You just have to think through theoretically, like, what's my model for change? What do I think is going to happen? How can I model that, right? And that's, I think, what makes these models super fun, but it also makes them you know, a little bit complicated. Yes. I mean, I'm not even going to comment on that because I don't do research with income versus adjusted income. So I feel like that's a question you should probably ask your advisor, right? I'm just really showing you kind of how the modeling stuff goes. I'm not going to comment on like how to use adjusted income versus income because I feel like I could totally step in it there. But the idea, I think the idea here is, right, income, whether adjusted or not, could be a level 1 variable or it could be a level 2 variable depending on the way you've collected the data and also depending on how much within person variability there is. So going back to my SES example, how could I diagnose whether a variable has enough within person variability to be a good level 1 predictor? So let's say I got my ECLSK data, right? I got that SES variable measured across 4 or 5 time points. And I want to know, should I be using it as a level 1 predictor or should I be using it as a level 2 predictor? What would you do if this were your data? Because this could be your data, theoretically. I've got a variable, it's measured across time. I suspect there might not be all that much variance across time in these data, but I'm not sure. What could I do? Yes. Need your bonus points back. Yes, that's exactly what you would do. You would run the unconditional model, right? And you would get the ICC for the predictor so again, I don't personally with growth models find the ICC to be all that useful with the outcome variable. If I know I want growth, I know I want growth. That's kind of where I want to start. But I find the unconditional model to be super useful when I'm thinking about predictors. If I'm not sure whether there's enough variability to model or not, so let's say it's SES and I run an unconditional model. I get the ICC for SES. And let's say I find that the ICC is I think in this case, when I did it was like 0.85, right? So that's huge, right? That says 85% of the variance in SES is between people and only 15% of the variance in SES is within people. And then you have to make a decision about magical number, like how high is too high? I would say once you get above 0.8, you're probably looking at something you should probably consider a time invariant predictor, right? But, again, and I think I say that in I think I even say that in the chapter that I wrote. But again, that's just sort of like it's like a rule of thumb. That's not a statistical necessity necessarily, but obviously the closer you get to 1, the more seriously you should consider it a time invariant. I mean, obviously if it were 1, it has to be a time invariant predictor, right? And so the closer you get to 1, the more you should be leaning toward time invariant predictor. Does that make sense? Yeah, time invariant predictor is level 2. So time varying predictors go in at level 1. Time invariant predictors or time invariant covariates go in at level 2 because they're at the person level. So if something doesn't vary across time and it does vary across people, it's going to go in at level 2 of our longitudinal model. If it does vary within person, it goes in at level 1. And that's why time has to go in at level 1 because our time variable is varying across time within person, right? We're good? Okay, let's see. How are we doing here? Okay, so here's my example where I put in a time invariant covariate. So this is a level 2 predictor, right? And the example here is like male. Let's just say we had, something that's dummy coded male or not male. And so I put that predictor in at level 2, and you can see, right, that effective male average or the expected effective male not 1 on the randomly effective being male intercept. This is the effective being male on the growth slope. And so this is really, again, it's a cross-level interaction because it's the effective male on effective time on the outcome. So it's still a cross-level interaction, but I think for some reason people find these cross-level interactions maybe a little bit easier because it's really the effective male on the growth slope. Effective male on the intercept, the effective male on the growth slope. But you can see we get the same thing here, the cross-level interaction. We end up with theta 1,1 times male times time. Right? It's that's our cross-level interaction. Questions about this? Sense? I feel like we kind of like talked about this a bit before we talked about it. So, okay, so this is just a really general slide that's saying like we could have a whole slew of X's, right? They're characteristics of a person's background. And I say it could be an experimental treatment, but again, it's important to remember an experimental treatment could also be, you could have a within subjects design or a between subjects design. So when I say experimental treatment, I'm thinking of a between subjects design here, right? Yeah, okay. So that's just sort of general, sometimes people see, okay. So back to the treatment of time. So again, time represents either, again, we can sometimes use time, sometimes we can use age. I'll talk a little bit about why age can be nice. But time represents time t, right? Or that time variable could literally be somebody's age at time t for person I. So that's that time variable. And we said each person can have their own growth trajectory that's defined by their own intercept and slope, right? But we can have variability in the number of time points. We can have variability in the spacing across time points. When we use time unstructured data, we can, I mean, that's what's kind of really important because with time unstructured data, it's really that sort of the spacing between time points is going to be different for each person. So you're really sort of much more accurately clocking the passage of time when you use time unstructured data than when you use time structured data, unless with time structured data, people really do have the exact same time schedule, right? So like with time structured data, if people vary by up to a month or two in terms of when they show up for those follow-ups, I'm going to call everybody 0, 3, 6, and 12. But if some people are 2 and some people are 4, but I'm calling all of them 3, I'm basically saying that the difference is 3 months, when for like person A it was only 2 months and for person B it was 4 months, right? So not having that time unstructured setup really allows for me to get a much more exact, precise measurement for time, which allows me to sort of fit the growth trajectory better. And I'm going to show you an example of this actually with the data that we use. And again, we sort of accommodate, we are able to do all this because we're using what's called a univariate perspective, or we're using a sort of long format data. So this is where the data setup is going to seem a little bit odd. It probably didn't seem odd when we were doing clusters. We had people nested within clusters, and each person had their own row. But in a longitudinal model, if we're going to fit a multi-level model with longitudinal data, the person is the cluster. And the observation is, like we have observations across time clustered within people. So that means I'm going to need to restructure my data file so that each observation is a row of the data file. So like if I have 3 time points per person, each person's going to actually inhabit 3 rows. I'm going to have 3 rows of data. I think I have a picture of this actually. Yeah, here we go. Here's a picture. So for example, we've got the ID variable. So this is like 3 time points per person. So the first person is person 68. And we've got, like here, age is not centered yet, but age is like 1, 1.5, and 2, let's say. And COG is some sort of a cognitive test. And you can see their scores on the cognitive test. And so you can see that person 60, right? Normally, often we would have person 68. It would be what we call a wide data setup is person 68, and I'd have their age at time 1, and I have their score at time 1, and I have their age at time 2, and I'd have their score at time 2, right? and I'd have just one row per person. But to actually model these data, I'm going to have my data set up in what's called a long or a univariate setup, or it's also sometimes referred to as a person period data set. Those are all synonymous. So univariate, long file, person period data file. That means each observation becomes a row. You don't need to leave empty rows for missing time points. And the rows are linked by the ID variable to the person. So the person ID variable becomes like our cluster ID here. So, and I think the data that we give you for homework this week is already set up this way, so you don't have to worry about you don't have to worry about doing this. But again, it is a really important thing to be able to do with your own data, because if you have a wide file, you're going to need to make it a long file, right? But you don't have to do that for homework. All right. So this is important. It's a really sort of a different way of thinking about structuring your data. So, actually, let's talk about centering time for a second. So remember, intercepts are always the value, right? The intercept is the value, like in this case, the value of the pi sub not I, when all of the, or the beta not, right? If we're thinking sort of at the general sort of model prediction stage, when all of the predictors are 0. And now let's just go back to only having time in for now. We'll deal with the whole time varying covariate thing next week. But to have a meaningful value for the intercept, we have to center time. And this is really, really important. If you don't center time in a good sort of meaningful way, then you're going to throw out information about your intercept, right? And so you'll like have this parameter in the model that's like not doing anything for you. And of course, if you haven't thought that through, then you're also going to lose. You're actually going to throw away 3 parameters, because you won't, your intercept becomes sort of meaningless, and then the variance of the intercept is also going to be problematic, and then the covariance between the intercept and the slope. Those 3 things are all going to vary depending on how you center time in your longitudinal model. So going back to our example of, like, let's say the example that we're going to use actually in class is reading growth from ages like 6.5 to approximately 6.5 to approximately 10.5. So we've got every 2 years, we have reading data on a set of 89 kids. So sort of at, let's say, what, 1st grade, 3rd grade, and 5th grade about. So if they're around 6.5, around 8.5, and around 10.5, and let's say I wanted to well, there are a bunch of different ways that I could actually think about centering time. So what are some things I could do? I've got 3 waves of data. They're roughly 2 years apart on these 89 kids, and I want to make a time variable. What could I do? Okay, I could center at start, right? So if I have 3 waves of data, let's say it's wave 1, 2, and 3, right? So I've got waves 1, 2, and 3. Waves 2 and 3. But like, said center at start. I know let's just, for the sake of argument, say I didn't center at start. If I didn't center at start and I just used waves 1, 2, and 3, what would my intercept be? Well, everybody starts at 0 in terms of waves, right? But let's just say I didn't. If I didn't center though for a second. Yeah, exactly. If I left it this way, the predicted score would actually be 1 wave before the start of my study, right? So if I said that I'm measuring them at like 6.5, 8.5, and 10.5, if I just used wave as 1, 2, and 3, then actually the intercept would be like, again, it would be linear extrapolation beyond the range of my data. I'm assuming I've got a linear slope. So it'd be the kid's predicted score at age 4.5 on reading. What would be some problems with that? There are a couple. The first problem would be, yeah, okay, first real problem would be like most kids are not reading at age 4.5, right? So what do you think, like, so that would be a bad place to center my data. If I'm looking at reading scores, I don't want to center at a place where nobody's reading because, again, now it's a linear model, so it might go negative or something, right? Because I'm extrapolating outside the range of my data, but I wouldn't expect to see a lot of variability in the intercept at age 4.5, right? So I'd expect that intercept now becomes kind of a throwaway because nobody's reading. The variance is a throwaway because there's no variance because nobody's reading, right? So that's a problem. And the second problem is that I am extrapolating beyond the range of my data. And because I'm fitting a linear model, there's no guarantee that if you extrapolate beyond the range of your data that you're going to get anything that's sensible, right? So for example, if I fit a linear model and it looks like this, let's say at 6.5, whatever, and then let's say I extrapolate down to like, let's say I've got data at ages 6, 8, and 10. I've got data at like ages 6, 8, and 10, let's say, but then I want to extrapolate to age 0, for example, right? Because it's a linear model. If I extrapolate down to age 0, I might actually predict a negative score on that test. And that doesn't, of course, make any sense either, right? So you want to center somewhere that's like reasonably in your, so there are two issues. You want 0 to be interpretable and make sense and not be a throwaway parameter. You also want it to be in the range of your data because you don't really want to center and then be extrapolating outside the range of your data, even if 0 does sound like a meaningful value, right? So like, even though 0 here, age 0, that makes sense, but I don't want to, well, it doesn't make sense for reading, but I don't want to extrapolate outside the range of my data. So I want to center somewhere, and it could be, let me be clear. You might use something where, let's say I center at age 6.5, and maybe most of the kids in this study are somewhere between 6 and 6.75 years old, and you center at age 6.5. And there's some kid who technically was 6 years and 7 months, right? And now it's gonna be his predicted score at 6.5. Am I gonna like lose sleep over that? No. I mean, a couple kids who are like, slightly outside the range of the data, okay, I can deal with that. But I wouldn't want to center at age 5 if all kids are getting their first time point between ages 6 and 7, right? That makes sense? Okay. All right. So to have a meaningful value for the intercept, we have to center time. At center time, we can center. There are lots of things we can do. We can center again. We can pick if we're using ages, which I'll show you. We can center it at a particular age. If it's waves, I can just center at a particular wave. I can center it at the start of the study. Maybe it's when people come into the study or at initial status. But again, it doesn't always have to be at the beginning. I could center time at the end of the study. What would be a reason for like centering at the beginning of a study versus the end of a study? Let's say you're doing an experimental study. What would be a reason for centering at the beginning? What might be a reason for centering at the end? Yeah. Well, I was thinking, if you center, let's say it's an experimental study, right? And you've got people at waves 1, 2, and 3. If you center at the beginning of the study and then you put treatment in at level 2, let's say it's a time invariant covariate. Now the treatment effect, right? So the treatment moderates the intercept. So this is going to tell you about whether there are differences between treatment and control people at the outset of the study. Why might that be nice? I randomly assign people and I want to make sure there aren't any treatment differences at the beginning of the study, right? So that could be a really good thing. But on the other hand, why might it be nice to center at the end of the study in that same situation? Yeah, I want to see if the treatment was effective. And so I want to look at their growth rate, and I also want to look at where they end up, and I want to see if there are treatment differences in terms of where they end up, right? So like it's two very different rationales. Like they're both interesting. I would like to know that, ideally, I'd like to know there weren't differences when they started out, and I'd like to know that there were differences in terms of where they ended up. So again, depending on what parameters you want out of the model and what you want to look at, then you want to think about how you center. Okay, so back to our centering here. So I've got waves 1, 2, and 3. I'm not going to just put it in as waves 1, 2, and 3. Okay, hold on. Mine's all falling apart. Jesus. I don't know what to do with all these pieces. I'm gonna put it together. Okay. So let's say I do want to center at the beginning of the study here, right? So instead of having waves 1, 2, and 3, what would I do? I want to have the first wave be 0, and then it would be what? Yeah, so I could just go like wave centered. Let's say I call this wave -1. My new variable is literally just going to be wave -1, right? This is not tricky. So I subtract 1 from each of these, and then I'm going to get wave -1 is going to be 0, 1, 2. And now wave is centered at the first time point, right? So I'm literally, I mean, that's easy. This is time, in this example, I have like time structured data or whatever. And I'm just going to subtract 1 from each time point. So I'm going to, and this is what I would want to use in the model, right? I wouldn't want to use wave. I'd want to use the centered version of wave. Does that make sense? What about if I wanted to center wave at the end of the study, like the example I just gave? So I really want 1, 2, 3. And what I'm saying here is I want my new variable to be 0 at the end of the study. Yeah, I mean, this seems weird to people at first, but it would be like -1 and -2, right? Because that's exactly right. It would be 1 - 3, 2 - 3, and 3 - 3. And why is it negative? Because I want time, I need time to increase, right? Like it would be really weird to go like,
So let's go left to right.
yeah, exactly. I want to go left to right on my time variable. That's exactly right. I want time to be increasing. So if I went time is 2, 1, 0, I'd be saying that'd be really weird. I've got time decreasing. Don't do that. So here would be, if I wanted to center at the last wave, I would go time is equal to -2, -1, 0. And so now I'm still clocking the passage of time where a 1 unit increase in time, right? I still am talking about the slope as being the change in y per unit increase or change in time, right? Yeah, but again, it's a linear slope, so it's not going to matter. You're going to get the same slopes. You're going to get the same growth rate, but now you're going to get the slope is just going to be the growth rate, and the time variable is just going to be centered. It's like how fast do people grow, and what's the predicted score at the end of the study, right? So that's fine. How might that change? Remember, we've got tau not, tau not 1, and tau 1, 1. So I just said it's not going to change the growth slope if I use this versus this, right? Will it change the variance in the growth slope? Oh, that is true. That is absolutely true. There's often more variability in terms of where people end up versus where they start. Would that be reflected in the variance in the growth slope? Not in the slope, right? Because the slope is still linear. I'm assuming a constant rate of change across time. So the tau 1, 1, I would expect to be the same, whether I center here or here. Doesn't matter. Tau 1, 1 is going to be the same, but what's going to be different? You hit the nose. The intercept variance, exactly. The intercept variance is going to be different because if I think, for example, let's imagine that I think that this is kind of, and this is actually kind of how reading growth does work. So maybe I think, right, that there are different slopes for different folks. And you can see here, if you think about, if I center here, right, look, that's going to be the variance in the intercept. If I center out here, right, this is going to be the variance in the intercept. So the variance in the intercept is absolutely going to depend on where you center the intercept. And yeah, generally speaking, if I think that people are getting, like more variable across time, and if I think, especially if I think there's a positive relationship between where people start and how fast they grow, blah, 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 then I'm going to expect to see, more variability at the end than at the beginning. And so I would expect the tau not, if I center this way, to be much, again, that's my example, tau not here is going to be much larger than the tau not here. Oh, that is true. That's true. I mean, absolutely. This is where it's really hard. I'm just showing one example where we would expect that, but absolutely there are other examples where the phenomenon that you're looking at would be something where you actually expect people to be more similar at the end than they are in the beginning. Absolutely. Absolutely. But the point remains that tau not would not be the same at the beginning or the end either way, right? It could be, in one case, it would be bigger at the end, in the other case, it would be smaller at the end, but it's going to be different. So what does that mean for tau not 1? Because I just said tau 1's going to be the same, but tau not is going to be different. So would tau not 1 be the same or different across the two centering strategies? Different, exactly. So where you center is going to influence what the intercept is, right? What the variance of the intercept is, and what the covariance between the intercept and the slope are. Look at, like, what time is it? Break time?
Mm-hmm.
So what
you can read my books now.
I can read your
like clear my watch.
Okay, I really want to finish. I think we're pretty much, we did that one. We're not going to talk about time varying covariance today. We already did a little bit.
It's actually almost 10:40.
Yeah. So, and we already talked about this. So I think I just want to make sure, I want to be able to like say, we're done with this. We're done with our slideshow for today. So we'll take a 10-minute break. And when we come back, we're going to run some models in R.
And if anybody didn't get the R marked down, I have copies here.
Okay, so let me see. Oh, and before, make sure you haven't already done so, like download the stuff, data and such. And follow along. have my mic off. Sorry, people in the back, people in the audience. I didn't realize the mic was still off. Okay, we're looking at our data here, and we really haven't done anything yet, though. We're going to look at individual growth trajectories. So here's some code to plot individual growth trajectories. It's always a really good idea. We saw some last week, right? I showed you like a panel of individual growth trajectories, and those were actually from the PIAT data. And I'm going to display all 89 of them at once. And so they're going to be really tiny, but what I'm going to do is make some growth plots, individual growth plots. And the easiest way that I know to do this is to do an XY plot. And I'm really just saying I'm going to use, right, the PIAT score is going to be a function of here. I'm using that wave -1 is going to be my X variable. PIAT is going to be my Y variable. And then I want a separate little graph by ID. So that's what the /ID is, which is actually looks a lot like the way we write our code for multi-level modeling. So I think that's actually kind of intuitive at this point. You know, I probably am a little redundant here because I say data equals PIAT, but I also told it that it's coming from the PIAT data file. And then this type equals CR means I'm graphing points, that's the P, and I'm going to graph a regression line through those points, that's the R, and I want the color of the line. You could just, but I'm saying that the color of the line is dark red. The LWD is like that's like the width of the line. So I'm telling it that I want, and you could mess with that, like try 1 or 3 or 6 or whatever, and you'll see that the width of the line will get bigger or smaller. You could change the color of the line. There are probably lots of other things you could do to make this prettier, but you know, I'm not going to. So that's the basics. And there we go. So this is kind of nice. So the first thing I would generally want to do before, and again, I mean, I'm expecting a straight line. I only have 3 data points, so it makes sense to fit a regression line to these data points. But if I had a whole slew of data points and I didn't think it was going to be a straight line trajectory, I wouldn't necessarily want to fit a linear trajectory through the data points. I might want to do like a lowest curve or some sort of a polynomial or whatever. But here we can only have linear, so that makes sense. So okay, so let's take a look at our little. You probably see them better on the screen than you can on your other one. Okay. Got an error.
Yeah, it said I didn't have X.
Yeah, it's lattice.
Okay. Oh, I didn't install a second.
Okay.
Never mind, sorry.
So here we go. What do you notice? Just, I mean, this is kind of nice. We can look at all 89 at once. Let's look sort of across. What do we, because remember what the questions are that we're going to ask when we run the multi-level model. So we want to get a sense of what we're seeing before we ever do the modeling. This is important, by the way, because then you kind of know what to expect. So looking across here, what would you say? Like, what might be a reasonable sort of average for the intercept? I mean, what? Oh, well, let's say we're centering at wave 0. So think about let's say that, yeah. So we use wave -1. So let's say we're centering at wave 0. So it's going to be, this is 0. So it's really kind of where it is the intercept. It's where it's hitting that left-hand side, right-hand, whatever. So what do you think? 20-ish maybe? Again, I don't know the exact number, but feels like it should be around 20 maybe. Does it look like people all start in the same place? No, I mean, definitely looks like there's variability across people in terms of where they are at time 0 or wave 0, right? How about how much I mean, I'm not going to ask you to guess about the between person variance. That would be cruel. And I would not expect you to be able to do that. But it does look like there should be between person variance, right? And where people start. How about rate? Again, probably hard to guess what the growth rate is because these are really small, but would you think it would be positive or negative? Positive, definitely. I mean, probably, like, again, I don't know, that it's not so easy to tell, but maybe a few points, right? Like maybe 10-ish points per wave.
Person.
there is a negative person again. So when on average though, we would expect to see something positive, right? Something positive and maybe something along the lines of they're starting at 20 and going to what? Hard to tell. I don't know. You don't have to guess, but definitely we'd expect positive on average. But again, is there variability in those growth rates? Yeah, I mean, we see a couple people are negative, which is super weird for reading growth from 6 to 10. I'd be very worried about like this kid. Where's the negative kid?
60, 78,
78, 70.
top right.
Yeah, really worried about that kid. Right, something's going on there. In general, it looks positive, right? People are growing in terms of their reading, but there's definitely a fair amount of between person variability in terms of how fast they grow as well. So, okay, so this is really, really helpful to kind of get a sense of your data. And I think in the homework, if I remember correctly, we do ask you to produce, don't we, an individual growth plot, something like this. So, but again, I mean, I can't stress enough how important it is to really, especially because, I mean, now it's got to be linear, but as we go through more complicated models, you've really got to kind of have a sense, you should have a theoretical sense of what the right growth trajectory is, but you also need to kind of know what your data look like too. Okay. So I've already explained the general information about the PIAT data. We've already talked about that. Okay. Now, in terms of creating these centered versions of the 3 age variables, the PIAT reduced, it just doesn't have, I think it does have those variables in it. There's another data file. We could write over what we have too, but PIAT reduced that I just read, and then these, it's going to be really, well, first, we don't have any missing data, so that makes it super easy. But the other thing that's really easy here is that for the time variable, we'll have to think a lot more when we're doing time varying covariates next week about group mean centering and gram mean centering again, so don't get too comfortable. But at least for this week, we're in good shape, right? Because we really are going to want to use the same, like when we centered, we're just subtracting off the same thing for every person, whether we're doing time structured data or time unstructured data. It's like the person's score, like the weight score or the age group score or the age score minus whatever. Like you could literally write, so you can see here, I wrote like age underscore 6.5. This is the one that wasn't in the data file I showed you, had age minus 6, but then I said like maybe I want to center at 6.5 instead. So I can just say like, right, you take age underscore 6.5 equals age minus 6.5, because I want to subtract 6.5 from every score. So that's really nice, right? That's like super easy, kind of foolproof. I think we actually have created all the centered variables for you for the homework this week, so you don't actually have to center the variables, but I want you to know how to, because it's really important. And you can see for the time variables, the centering is, right? So here I've got the 3 variables that I created. So here we've got like, you know, this one I just talked about, and I can actually do all 3 in one command by just separating with commas. So I've got age is age minus 6.5, age group minus 6.5 is age group minus 6.5, and wave minus 1. I'm using the underscore in my mind. It's like wave minus 1 is wave minus 1. So if I do that, I get all my centered variables. Okay, so then I think it's always kind of useful to be knowing a little bit about the descriptive statistics. So here, I'll just run this. These are descriptive statistics for the PIAT score across both time and students, but I would argue this is not as informative because I haven't broken it out by wave, right? So if you think about it, when I gave that example of like if I fit the completely unconditional model where I just have like no time slope and I just fit like an average, sort of an average for each person across their time points, that's kind of what this is like, right? So this is saying that like on average, across ages 6.5, 8.5, and 10.5, people's PI mean scores are like 31, right? But that's like, again, okay, that's interesting, but it doesn't tell me anything about growth, right? And on average, I now know that like the standard deviation of PI scores is about just under 12, right? And the variance is 142. But like, again, I think that there is growth, so this is not as interesting. So what I really want to know is what the descriptives look like by wave, right? That's far more interesting. So the first thing I can do is just, filter by wave. So I just created like Fiat wave 1, just Fiat filtered at wave 1, Fiat, it's not Fiat W1, Fiat W2 is Fiat filtered at wave 2, and Fiat W3 is filtered at wave 3. And this is one of those things, and again, where you have to, when you have a long data file, some of the things that are so easy in terms of descriptive statistics are like a little bit more difficult now because you want to know what the mean is at wave 1, but like, because you've got a long file, you really have to just be selecting the rows that are wave 1 rows to be able to look at what's the mean. So that's the logic behind why I'm doing it. That makes sense? And so now, because
Selecting cases.
yeah, I'm selecting rows is what I'm doing, right? So I've created sort of 3 different things here. This is like the rows at wave 1, rows at wave 2, rows at wave 3. And now I could look at the means just for wave 1 and the standard deviations just for wave 1, the means for wave 2 and the standard deviations for wave 2, for wave 3 and the standard deviations for wave 3. That is going to be a far easier for me to like think about what does growth look like if I know what the means are across the 3 waves versus just knowing the overall mean is 31. Doesn't tell me anything about growth. Now, of course, this is your own data and you have it in the wide file. You could just run the means across wave before you transform it to be a long file. And I find when I'm doing my own data stuff with longitudinal models, I find that I do all my screening and cleaning first, usually the wide file. And then I create a master wide file and a master long file because there are certain kinds of graphs and things that are just going to be easier for, even though you're doing multi-level modeling and you need a long file, certain things are going to be easier in the wide file and certain things are going to be easier in the long file. So like when you're doing your own data, my suggestion would be first with just one file, make it pristine, as clean and beautiful and sparkling as it can be. Then transform it to be a long file. When you do that transformation, you should be done with all the hygiene, because if you don't, then you have to do it twice, right? You don't want to do that. And then keep a master wide and a master long, and you'll find yourself going back and forth between them for a variety of reasons. But okay, so here I got to filter by wave. So now I want to look at the means of each wave. Oh, I just run this. Bad. Now I can look at the means of each wave. And here you go. So this is, I think, useful to look at because now, remember, I was asking you like, how much growth see on those little plots. But now if I said to you, again, remember, we're going to fit a linear trajectory. So like how much growth do we think we might like, for 1 unit change in wave, how much growth do you think well, it looks like from wave 1 to wave 2, we get a change of about what? 20 half or something, right? Is that right? But from wave 2 to wave 3, we get a change of about 18 and a half, something like that. But remember, I'm fit. Do you see that? Like, oh, sorry, 12. My bad. Yes, I don't know why I'm saying 21 and 18. 12? Yeah. Mental arithmetic this time of day, not going so well. Okay, 12 and 8. So 12 and a half and 8 and a half. But remember, I'm not fitting a model where I'm going like 12 and a half and 8 and a half. I'm going to fit a linear model. So what do you think? Am I going to be point something as a linear growth slope? That seems like a really like a good prediction, right? That my linear growth is going to be like 10 point something. Which again, I cannot encourage you enough to like, just these little simple things will help you as a check when you actually go to do your modeling, right? Because if you kind of have like an intuitive sense of the mean should be and like what kind of shape you're expecting, it's going to help you so much when you go to do the model. Okay. And also to be able to see, does my intercept make sense, right? So like if I ran my model and my intercept were 100, I'd be like, whoa, that seems crazy, right? And if I didn't have kind of a sense of my data, I might not know that seemed crazy. But obviously 100 would be crazy. Then I know something has gone amiss, right? You know, again, we can run variances in this in each wave. I think the thing that's interesting in longitudinal models that's important to kind of keep in mind, or is like, not surprising, what you see is that the variance is getting bigger in each wave. Right? Which, you know, so, which makes sense. You know, at the first wave, most kids are just learning to read, so there's less variance in terms of their reading skills. By the time we get to the last wave, the variance in the reading skills is much higher. That's good to know, although maybe not as predictable as the mean right now. All right, so here we go. Let's run a model. I'm so excited. So here's our unconditional growth model. So we've got P on at time t for person I is a function of, right, the intercept plus our pi 1 sub I times time plus e sub ti. And then in our level 2 model, this is our unconditional linear growth model. So we don't have level 2 predictor yet. So we're just gonna, but we are allowing for, and again, normally we would always allow for randomly varying intercepts and randomly varying slopes. What if I took out the r sub ij? What would that be saying? What would my model be saying if I only allowed for randomly varying intercepts? Yeah, there are no between person differences or no between person variance in the rate of change. So I'd be saying all the regression lines are parallel to each other. Different people start in different places, but they all change at the same rate, right? That's what this model would say. Got this. What if I allowed for the r sub 1j and took out the r sub not j? What would that be saying? Yeah, everybody starts at the same place, but they grow at different rates. But if I want to say people can start different places and grow at different rates, then I'm going to need these two. Yes, question.
So is what you're saying is that there's one slope here, but you have slope, like varying slopes that are not randomly.
Oh, sure, for sure. And in fact, I think if we get far enough in this example, we could see where that might even make sense in this example, that once we put in one of our level 2 variables, you know, we could ask ourselves, do we need the randomly varying slope anymore? Yeah. So at the outset, for sure, before I have predictors, I'm generally going to default in a growth model to allowing the intercepts and the slopes to randomly vary. But I mean, if you think about it, your goal might be, although this never happens, okay? So this is like pie in the sky here. But you could imagine that, like, if you had a really great model where you had these awesome level 2 predictors, that like maybe your goal would be that you have this great set of covariates that can actually explain all the variability in terms of where people start and how fast they grow. And if you have this awesome set of unbelievable predictors that tell you about why people are different in terms of where they start and how fast they grow, maybe after you put in all of those predictors, you wouldn't need either of these things. That would be cool. Again, does that ever happen to you? I hope so, but I doubt it, right? Like, it sounds good, like in this utopian paradise where you have these awesome predictors, though, right? Maybe, and that's what, if you think about what happens to the between person variance in the intercepts, that tau not, and the between person variance in the slopes, as we add good predictors, the between person variance in the intercepts gets smaller, right? Because it's residual variance and we're explaining it. If those are good predictors, if they're not good predictors, maybe we're not explaining it. But you could imagine a situation where if I had a great set of predictors, I might be able to explain really why people are different in terms of where they start and how fast they grow. And I don't need those residuals anymore. But again, that's kind of like saying, if I run a regression model, right? Like just a single level regression model. If I had the right set of predictors, maybe I could explain virtually 100% of the variance, and the residual variance would go down to 0, which is theoretically possible, but it never happens. And just as an aside, I actually, when I was editor for a journal, a paper came in and we accepted it. And then after the fact, somebody said they thought it needed to be retracted. They suspected foul play. They suspected that the data were fabricated. And they had gotten a copy of the data from the author. And so they sent the data to me as the editor to look at. And I ran regression models. Like so it was like a treatment thing. So it was like treatment and control. And there might have been one other covariate. Anyway, I ran these simple, I ran a regression model. And the regression model explained over 99% of the variance in the outcome variables. This was not simulated data, by the way. It's just like fabricated data. Because if you simulated data, it wouldn't look like that. Somebody literally just was like, this should be what this is. So anyway, so I ran it, and again, my simple regression model was a multiple regression model, but it was a simple one. It explained over 99% of the variance in the outcome variable. And at that point, I was like, yeah, absolutely, this is fake. Because nobody with two variables, like one covariate and treatment, nobody explains over 99% of the variance in their outcome variable. I don't care, right? So we retracted that paper. And that was one of the main pieces of evidence that I used when I talked to the authors. And of course, they were just like, they blamed it on some poor grad student in another country that wasn't there for the meeting. Sorry. I know, isn't that depressing? Yeah, all right. Anyway, I digress. Point is, so theoretically, it could happen, but it's not going to happen. But moving on. So time, I'm not going to read to you everything that I've written here, but we talked about time structured versus time unstructured data. And I'm going to show you now, I think, why doing time structured data is advantageous. It should already run that code. Okay, here comes our model. Oh yeah, so here's our combined model. We didn't look at that, but here's our combined model. Oh, no, wait, I can do that. There we go. By the way, just notice here in these models, I'm actually using REML equals false. So I'm running all of these in FIML. Oh, I see a typo too, which I tend to use FIML a lot for longitudinal models, not so often for organizational models. Why do you think I might do that, by the way? You know what we talked about, REML and FIML way back. Anybody know? REML and FIML are going to be very similar if you have a large number of clusters. But where they're going to deviate is when you have a small number of highest level units. And REML will give you more accurate estimates of the variances. Once you get to a sort of a reasonable size of level 2 units, it's not going to make too much of a difference. Again, kind of analogous to with variances, do you use the sum of squares over n versus over n minus 1 makes a huge difference if n is 20, makes not so big a difference if n is 100, right? So same kind of logic here. Well, with longitudinal models, people are the cluster. So for longitudinal models, we often have a very large number of clusters. We don't have as many observations per clusters, but REML and FIML will tend to, unless you have a really small longitudinal study, then you probably got problems. But so it's not going to matter as much. And from a model fit perspective, it's kind of nice because remember, I can't compare models that differ in their fixed effects with things unless we use FIML. So I'm using FIML here, and I'm not so worried about it because I got a decent number of clusters. But in organizational models where you often only have 20, 30, 40 clusters, I'm generally always going to use REML. Okay. All right. Here it is. So let's get our fixed effects. And this is very comforting because we said that the intercept should be something around 20-ish, didn't we? And our intercept is actually 21.16, right? So the average score at age 6.5 is 21.16. And remember, we said our slope would probably be about 10-ish points, right, per wave, which is a 2-year. Remember, a wave is 2 years. It's because it goes from 6.5 to 8.5 to 10.5. So this wave is for every 2 years of increase, approximately 2 years, because it's time structured. So for every approximate 2-year increase in time, we expect kids' scores to increase by about 10 points. So what would we expect the yearly growth rate to be? 5, exactly. We just cut that in half, it would be about 5.03 points, right? So if I use that age group variable, I would expect to see this estimate be cut in about half, but my intercept should be the same, right? And yeah, okay. So there we have that. I don't think we need to really do anything with effects right now. I mean, I'm just showing you. I could save my fixed facts. There they are. My variance components. That's my variance components here. Oh. Okay, so here are my variance components. Okay, yeah. Okay, so here are my variance components. So you can see here, and you could look up at the summary too. Here's the between person variance, and the intercept is about 11 points. The between person variance in the growth slope is about 17.5 points. And then the between person covariance is about 3.3 points. And then this is, remember where it says standard deviation here, this is actually the correlation. So this is the correlation between the slope and the intercept is about 0.24 points. And then my pooled within person residual is about 27 points, right? So those are my variances. One question I might want to know though is like, is it fair to interpret? Is it fair to interpret that covariance? So like, because I would be able to say something, well, let's say it is, let's just for now assume that it's fair to interpret that covariance. There's a positive correlation between the slope and the intercept. So assuming that is like statistically significant, or it's sort of, I'm estimating it precisely enough to actually interpret it, what would it mean to have a positive covariance between the intercept and the slope, the intercepts and slopes? Yeah, exactly. Kids who start out higher in terms of their reading grow faster. Actually, in the reading literature is called the Matthew effect, and it's pretty well documented. So it's not something that we find that. Okay. All right. So how we're going to interpret this, we are going to say, right, kids at approximately age 6.5 or at wave 1, they started about 21.16 points, and they grow about 10 points every 2 years, or about 5 points a year. And there seems to be a lot of between person variability in terms of where they start and how fast they grow. Okay. So what if I wanted to know, like, and what's the predicted score for a kid, a PIAT score for a kid at wave 2, right? Or what if I wanted to know what the predicted score for a kid who's like 7.5 years old? That's not the same as wave 2. Actually, here that would be like between wave 1 and wave 2. Well, I use this package. I actually make predicted values really easily by saying. We're not done this before. Understand. I showed you how to do it. Never gonna have to do what you did for homework ever again. Now that you know what you're doing, because I can just use all effects and watch this. How cool this is. Okay, so I say all effects, model 1A. Okay, here we go, and it's giving me the predicted values, and it's actually giving me at wave 0, which is the intercept. That makes sense. At wave 1, actually at 0.5, which is kind of nice. So that would be the predicted score at approximately age 7.5, right? Because that's halfway between 6.5 and 8.5, right? So the predicted score for a student who's approximately 7.5 years old in this simple model is like 26.2, basically, right? And the predicted score at age approximately 8.5 is 31.22, right? And the predicted score at age 10.5 is 41.28. Everybody with me? All right, cool. And I could actually compare those to the means that I got before to see how well my actual means sort of map on my predicted scores. Okay, so I could do this, but I could do this as a data thing and save it as a data frame. And one of the nice things about doing that is it gives you the predicted scores. It also gives you now the standard errors for those predicted scores, and it gives you upper and lower confidence intervals for those predicted scores, which are all things you couldn't get by hand before. So there are actually advantages to doing it this way, even if you love to do it by hand, because now you can actually get some. Okay, and then finally I can flip this, and again, this is using that same package, and it's there it is. Dun, da, da. So I said plot all effects model A, and it's not a very interesting plot because it's like one line linear, but the shaded part is actually that those are the confidence intervals. That's what that's about. So that's sort of telling you about the plotting of the predicted values. Okay. So that's all cool, right? And I could save, obviously I could save these predicted values. I don't do that right now. If I run this, let's see what time it is. If I run this as, I'll just run this quickly. If I run this, now I take out wave and I put in age group. Let's just quickly run this and look and see what we see. You're going to see, if you were to compare the model fit, it's going to be identical, right? Because these are mathematically, like they're statistically equivalent models. Here, though, we look at my fixed effects. The fixed effects, the intercept looks identical. The slope is now cut in half, which makes sense because now my slope is a yearly growth rate instead of an every 2-year growth rate. And my intercept variance is the same, but my slope variance is not the same. Did you notice that? Why is my slope variance not the same? Well, my slope is cut in half, actually. So my slope variance actually ends up being, if you look at it, what was our slope variance before? Let's see. 17 point something, was it? The slope variance, 17 point what? 17.59. And now my slope variance is, there it is, basically 4.4. Which is actually a quarter of the size that it was before. So this slope variance is 1/4 the size of the slope variance from before. Why? Well, variance is squared. It's a squared term, actually. So I chopped the slope in half. I'm actually, chopping the variance of the slope in like 1/2 squared, which is 1/4. But again, so maybe it looks different, but actually, like mathematically, no, it totally makes sense. Okay, so we basically get the same thing there. Uh-oh. Where'd I go? But where we really want to look is approximate. Okay. Here we go. Here we go.
What did we?
Model, the second model, all I did was I changed from the age, the wave variable to the age group variable. So now the time variable was basically 0, 1, 2, and now I'm using this time structured variable that's 0, 2, 4. So like all it really changes, essentially all it really changes is like the metric for the time variable. But, they're basically equivalent models, right? But I might prefer the second one because now I get a yearly growth slope instead of a bi-yearly growth slope, which seems a little weird. But now the important difference is let's try this time unstructured variable that's age minus 6.5. So this is time unstructured, right? So everybody's got their own data collection schedule. So here things might not look the same. So now again, for the model, all I had to do is swap out my time variable. So now I'm using age underscore 6.5 plus, again, I'm allowing both the slope and the intercept to randomly vary. So I've got the slope here, and by default, it's going to be the intercept. And I'm going to run this as model 1C. And now let's take a look and see how this changed. Oops. Where'd it jumping. Wait a minute, that's not the right, that's why. Week 7. I was like, that doesn't look like what we're doing. Okay, so run model 1C. Oh, did I not create age underscore 6.5? I did. Oh, I did it in the reduced one probably. Go back to that age. Age underscore 6.5. Back. Okay, coding time, blah, blah, blah. Oh, wait, did I do it before that? Create my, here it is. Okay. Yeah. Fiat, age underscore 6.5. Okay. And that's Fiat. So we should be good now. Maybe I didn't. Okay, so going back to 1C. 1C. 1B. Here we go, 1C.
By the way, try to plot 1B.
Yes. Oh, hold on. Plot 1B. Really? Plot 1. Oh, I know. Wait, right here?
Right there.
Yeah. Oh, I know why. You know why? So, this is an important little tip. So, here where it says false, that basically won't include stuff in the output. So, great for me, but if you take out the include equals false, and if you have the package installed, it should work for you. So there are a bunch of places where I put include equals false in here because I didn't want the stuff to show up in our on Markdown. Yeah, right. So take out include equals false, it'll run for you. Why it worked for me, I don't know. Maybe I get out by deep, like maybe I quickly did that because I knew without even realizing. Okay. So here we go. Time unstructured data. We now have our age underscore 6.5. And here it is. So we've got our summary statistics. And what do you notice is different? The intercept doesn't look that different, right? What was our intercept? It was 21 point. It's not the same, but it's not like radically different. What is different? Well, of the fixed effects, which fixed effect that is not the intercept is different? What do you think?
Super subtle.
Yeah. Slope, right? And do you remember before the slope was like, it was, you might not remember, but I'll tell you, it was 5.03. And now the slope is 4.54. Well, that's interesting. So my yearly growth slope is 0.5 point lower using the time unstructured variable. Why would that be? Any ideas? Where the first 1C? Oh, yeah, well, okay, well, I could have totally messed that up, and one might be where Remmel is false, and one might be where Remmel is, kind of go back and forth, so, yes, that could explain it.
Wait.
Yeah, so remember the time unstructured variable is like actually clocking exact time. The other variable was clocking approximate time, and if you even go back and look at, remember what our means were? Like the mean at the first time point was 6.45, I think. And then at the second time point, it was actually, if you look at them, it was more than a 2-year time. Like, what were our means? Hold on. We look back. It was 6.5. Or did I show? Oh, maybe I didn't show the means for ages. I only showed the means for Piat. Hold on. I think I got it next. Yeah, here it is. Okay. So let's look. The mean for age 1 is 6.45 with a standard deviation of 0.27. And remember, when I use time structured, I'm assuming there's no variance. Everybody's 6.5 with like a variance of 0, basically. For time 2, look, it's on average at time 2, people are 8. Like if you look
it's not, that's why I kept saying an approximate 2-year difference. It's not. It's actually like a 2.4-year difference between wave 1 and wave 2. And if I look at wave 3, that's closer, right? Let's see. 10.9. So yeah, it's like a little more than 2 years between waves 2 and 3. So like, it might seem weird at first that we lost a half a point of growth when we went from time structured to time unstructured. But the problem is that our years weren't really years. This is like the exact yearly growth rate. That was like an approximate yearly growth rate, but our approximate years were actually longer than real years. So that is like a really good reason to be using the time unstructured data. Yeah.
So the time.
Yeah, exactly. And then I centered it, and so then it ended up being 0, 2, and 4. It's like their actual age minus 6.5, their actual age minus 8.5, and their actual age minus 10.5. So you can go back and look in the data file and see how that's different. So we're getting a much more precise estimate of the slope because we're actually measuring change in time much more precisely. So is there a way that we could, could we compare the fit of these two models? Well, we could, right? Maybe I do that here somewhere.
It's
Is it
1B and 1C? Well, yeah, you do.
above or below?
Below.
I was gonna say, I thought it was below.
I'm looking at the printout, so.
I think it's above and below. Yeah.
Well, I've got the compare, hold on, let's see here. Well, here's compare. Let's just run this compare.
Well,
There's AIC and BIC too, but okay. But for now, we can just look at the compare. Because again, so we've got the deviance, and remember that the AI, well, first, can we use a likelihood ratio test to compare models B and C? No, because the models aren't nested, right? And one surefire way to know that is because they both have the same number of estimated parameters. So like anytime you've got two models that have the same number of estimated parameters, there's no way they can be nested. That means you must have taken something out and put something back in, put something else in, which is what we did. We took out one time variable, put in the other. So these are models that differ in terms of their fixed effects, which means we need to use Fibble to compare them. Right? But they have the same number of parameters. So this is a little shorthand. If two models have the same number of parameters, remember the AIC is the deviance plus 2 times the number of parameters, right? But if the number of parameters is the same across both groups, then 2 times the number of parameters is going to be the same across both groups. So you don't even have to think about that, right? So when the two models have the same number of parameters, the model with the lower deviance will have the lower AIC. And that's true of the BIC as well, because the BIC is the same thing. It's the natural log of n times the number of parameters. But if the number of parameters is the same across to the two models, then it doesn't even really matter what the natural log of n times the number of parameters is, because it's the same across the two groups. Or not groups, two models. So the model with the lower deviance is going to win, right? So as long as I've estimated these models in Fibble, I can look at this and say, whatever model, in this case, because the models have the same number of parameters, whatever model has the lower deviance wins. It's going to have the lower AIC, BIC, SBIC, CAIC, whatever IC you want, it's going to be lower for the model with the lower deviance, right? I could say for every information criteria, this one wins. Okay, so looking at the deviance, and again, you can see what I said, models A and B, they are statistically equivalent, right? So they have the same deviance, which makes sense. But model C, the deviance is lower. It's 16 points lower, right? 1804 versus 1820. So model C wins. With me? That makes sense? Which is another indicator. So there are a couple reasons that we might favor model C with the time unstructured data. Okay. So I want to make sure though that we get to a model where we have a predictor. Okay, so I talk about all that, blah, blah, blah. I will not show that graph, but you can look at it yourselves. Oh, wait. I got to do this because this is on the homework. This is an important idea. Not hard, but important. Plausible values. So I asked you on the homework, about a range of plausible values for the intercepts and a range of plausible values for the slopes. This is not the same thing as confidence intervals, right? By the way. So what I'm saying is like, okay, let's say the overall intercept was 10, right? But we know there's a lot of between person variability in the intercept. And what I'm asking you is like, what's sort of a plausible range of values then in the data for the intercept? And I could do the same thing for the slope. The slope is 4.5, but there's some amount of variability between people in terms of the slopes. So I want you to be able to give me, again, this is not a 95% confidence interval around the slope and the intercept. This is like, in my data, what is the range, what range of values might I expect to see in my data for those randomly varying intercepts and randomly varying slopes? Okay, so does everybody understand what the question is? Yeah, so again, I want to know, I know I have an average for people in terms of their intercepts and their slopes, right? I have an average, and I've been estimating these taus, these between person variances in the intercepts and the slopes. But I know there's a lot of between person variance, so I might want to be able to capture that and talk about that when I'm talking about my data. So if I'm saying the slope is 4.5 on average, and there's a lot of like, it's 4.5 on average, and there's a lot of between person variance. We've said that, right? We've got the between person variance estimate. But a person might say to you, okay, yeah, sure. On average, the slope is 4.5. But like, what's like a plausible range of values for the slopes in your data, right? Like you're telling me on average it's 4.5. You're telling me there's between person variability. I want to know from you, does that mean slopes generally range between 0 and 9? Do they generally range between 3 and 7? Do they, right? And that's not the same as a confidence interval. Because a confidence interval is like, okay, this is my estimate. What do I, like, given that the slope is 4.5, right? Like my estimated slope is 4.5, give me like sort of a confidence interval about what I think that the actual average, like this intercept for the slope is in the population. That's different. It's going to be much tighter, much smaller. This is saying, no. I know that 4.5 is the average, but I want to know how much between person variance, like I know there's a lot of between person variance. So even though on average it's 4.5, what's like a likely range of slopes I might see in my sample? So this is like a sample question, not a population question. And because it's a sample question and not a population question, what do you think I might use to solve this problem? I'm not going to use a standard error. If I wanted to know in the population, if I wanted to know, given my sample is 4.5, what's like, right, like I could then create a 95% confidence interval for the population value using the standard error. That's not my question. My question is, it's 4.5 in the sample. What's the likely range of slopes in my sample? I don't want to use a standard error. I want to use the standard deviation of the slope. So I would want to use the standard deviation of the intercepts and the standard deviation of the growth slopes. And I get those from my output. We've been looking at the taus mostly. I spend a lot of time talking about taus. Taus are great, yay, tau. But the standard deviation is just the square root of the taus. And it comes out on the output when you do summary, right? We see the taus, and then right next to it, we see the standard deviations, which are just the square roots of the taus. So if I want to answer this question, I could say, like, okay, my intercept was, well, I remember it was like 4.5. Let's call this 2 for a second, just to make our math easy, right? So let's say that, or 1.9. Let's say our slope. Let's say our slope is 4.5. Can you write this up on the board, Pam? So our slope is 4.5 on average. And the standard deviation of the slopes is 1, let's just call it 1.9. It's getting late. So 4.5 plus or minus 1.9 would give me 2.6, right? I actually did this all out. I think we've got the code. And isn't that 2.6 and plus was to 6.4? But now I only did one standard deviation. So what percentage of the slopes in the sample would I expect to be between 2.6 and 6.4? 68%. That's exactly right. So this gives me like a 68%, what I'm going to call a plausible interval. I'm not calling it a confidence interval because that's about parameters. And now, but what if I wanted like a 95% plausible? I'm technically for 95%, we should use 1.96, but let's use 2 to make our math easier for now. So if I wanted to get a 95% plausible interval, I would go 4.5 plus or minus 2, again, technically 1.96, but 2 times 1.9 exactly, which is going to be 3.8, right? And when I do that out, I'm going to get, what am I going to get? I'm going to get 1.3 on the low end, right? To 3.8 plus 4.5 is 8.3. 8.3, is that right? Check my math. It's a lot easier to do math when you're sitting than when you're standing in front of like 20-some people, I've noticed. Okay, so that's saying like, okay, the average slope is 4.5. I would expect 95% of the slopes in my sample to be between 1.3 and 8.3, which means, again, there are interesting things that I can say about that. That means I expect virtually all of the slopes, or maybe all of the slopes, all or virtually all of them to be positive, right? There's a lot of variability, but generally they're not, generally not going negative, right? Even like 95% of them I expect to be between 1.3 and 8.3. I can do a 99% if I wanted to. Does everybody follow the logic of that? So there's a whole set of code that I'm going to also do it by hand. You can do it by hand. There's a whole, it's easier to do by hand. I actually show a whole set of code if you wanted to do it. Like if you actually wanted to use, this is basically just using R as a calculator right here. Right? So I'm just like naming my intercept and my slope, and then I'm creating the confidence intervals. Honestly, if you don't follow this, just do it by hand. It will be way faster for you than trying to like worry about the R code. But that is the logic. Okay. So that's all of that. Now, model 2. We have to get to model 2 in the last 5 minutes together. Model 2. Okay, remember, LD is fake. We're going to put in LD as a predictor of both the slope and the intercept. Wish I had okay, so here's my code. Wish I had the equations written out here, but you can see here that the PIAT score is a function of, right? So we've got, I mean, again, I don't have to put all this in, but I'm saying, right, we've got the intercept for age, we got LD fake on the intercept, and now we've got this cross-level interaction, which is the effect of LD fake on the effect of the growth slope, right? And we're allowing for, I put 1 plus here just to remind ourselves, we're allowing the slopes and the intercepts to vary. No loop for break next. Anybody know what that error message means? What did I do? No loop for break next. What? What does that mean? That's so weird. Okay, I'm baffled. So no loop for break next, jumping to top level. That's so strange because I have run this already. Why on earth is it not running? Okay. PIAT, hold on. Data's PIAT, summary model 2. Does anybody see anything that looks wrong here? It ran for you, right? Oh my God. That's weird. I did nothing different. Okay. That's annoying, but also happy.
That's my experience.
Yeah, I know.
That's hard enough.
What I like to say, I try not to say in this class, but what I like to say for people is you get what you it's free. You get what you pay for. So, all right, but here we go. Let's make sure that we can interpret all of these fixed effects, right? And then we'll also quickly look at our variance component. So, our intercept is now 21.134. How would we interpret that intercept? It is the predicted value at age 6.5 for whom? Oh, LD fake, by the way, is coded 0 if you're not LD fake and 1 for LD fake. So 21.134 is the predicted intercept or the predicted score at age 6.5 for whom? When LD fake is 0, which means when you are not LD fake, right? Let's just say LD. So for students who are not LD at age 6.5, their predicted score is 21.13. What is the predicted score for students with LD at age 6.5? It's 0.21 less, right? So the predicted score for students with LD, like this LD fake, this is the differential between students with and without LD on the intercept. So if I want to get the predicted score for students with LD on the intercept, it would be 21.13 minus 0.21, which would give me 20.9 something, right? Is the differential between students with and without LD on the intercept, is that differential statistically significantly different from 0? No, interestingly enough, and that's what this is telling me, this negative 0.21. So yeah, I mean, it's a little lower for students with LD, but it's not statistically significantly different from 0. So what I would say is students with and without LD actually, again, remember I cherry picked these data, but students with and without LD actually have similar scores, or basically like they have similar scores at age 6.5. So you wouldn't necessarily, if you were looking at age 6.5, be able to distinguish the students with and without LD, right? Because they have similar intercepts. Well, but now let's look at the slope. Okay. Remember our slope before was 4.5, right? 4.5 something. Now our slope is 5.678. But why? It is the intercept of the slope, which is the predicted slope when LD is equal to 0, which means it's the predicted slope for whom? Yeah, this is the predicted slope for students students without LD are predicted to grow 5.68 points per year. Okay, what about students with LD? What's the differential? First, what's the differential in the predicted growth between students with and without LD? That's my cross-level interaction. That's right here, and it's -4, which means students with LD are expected to grow 4 points less per year than students without LD. That's huge, right? So we said students without LD, their predicted score is 5.68. It's 4.02 points lower per year for students with LD. So 5.68 minus 4.02 is 1.66, I think, right? Something close to that. So the predicted growth rate for students with LD is 1.66 points per year. And that differential is statistically significantly different from 0. So students with and without LD are starting at about the same place, but the students without LD are growing way faster than the students with LD. Does that make sense? With me on that? Okay. And then, interestingly, if I look at, now I have to compare what proportion of the variance am I explaining with my LD variable, right? And if you look, I'm actually not explaining much intercept variance with my LD variable, maybe not any at all. Why does that make sense? Why does it make sense that there isn't much of a reduction in variance between model 1C and model 2 in terms of the intercept variance? Yeah, because that LD was not a statistically significant predictor in the intercept, right? So it doesn't actually, I still have lots of intercept variance between person variance and the intercept. LD doesn't help me to explain it, which makes sense because it wasn't a statistically significant predictor. But I saw huge differences between LD and non-LD in terms of the growth slope. And so if you go back and you look at what the between person variance was in the growth slope for model 1C, and I don't remember what it was off the top of my head. Oh, no, I do actually. I think it was about 3.3, because I think we have reduced the variance by over 90%. I actually remember doing this when I was doing it. So it was I think it was about 3.3 before I put in LD fake. Putting in LD, the between person variance and the growth slope is now 0.3. And this is a case where, like, you know, like maybe who brought up the example of like, would you ever get rid of the randomly varying slope? Again, this is totally cherry picked, right? Like the example I gave when I was the editor. But in this cherry picked case, I might be able to get rid of the random component for the slope here, because I'm explaining pretty much all of the slope variance with LP, because I totally picked the low growth slopes and called them LD, which is why I made this data set. All right, so anyway, so in this like very, very fabricated case, maybe I could, and I could do the same model comparisons that we've talked about, where I could actually take out the growth slope and compare the fit of the models with and without the random variance component for the growth slope. One last thing I do want to say is I asked you in the homework, I want to point something out. Look at the correlation here. It's 1. That's really big. And I said we're often really interested in being able to interpret the correlation between the slope and the intercept. And when you see a correlation that's like 0.999, I think everybody would want to say, well, clearly there's this really large positive correlation between where you start and how fast you grow. But the thing is, I might not actually be able to precisely estimate that tau naught 1 parameter. It's not uncommon to find, in my experience, enormous covariances here that are basically not just a lot of noise, not very precise. So the one thing that I do show you how to do in this markdown file, I mean, you already know how to do this, but like what I would encourage you to do and what I ask you to do in the homework is to compare a model with the covariance and without the covariance to see if the model fit degrades substantially when you constrain the covariance to be 0. Because if this thing is for real, right? If it's really that strong a correlation, the logic is, if it's really that strong a correlation, then when I constrain that correlation to be 0, my model fit should go down a whole bunch. So and remember we can do that with the double bar. So I can use the double bar instead of the single bar on this model, and I can compare the fit of the 2 models. If on the other hand, I do that, which actually I can do, what's the deviance here? I need to find the deviance for me. Do this. If I do the double bar and I run this, what was the deviance? 1721, and now the deviance is 1723, right? Basically, and again, I walked through. In this, I walked through all of this, but basically, the deviance stays the same, whether I allow for that covariance or I constrain it to be 0. If that's the case, that, in my mind, is a sign that you should not be interpreting that covariance. It doesn't mean it is 0. It doesn't mean it isn't 0. It just means it's a really noisy estimate. You really can't say what it is. You just can't estimate that parameter precisely enough to say anything about it. Does that make sense? And so this is a place where, again, I've always said we want to default to estimating the covariance, but before I interpret the covariance, I want to check and make sure that it's like fair game to interpret and not just interpret something. Because like, again, it would be so tempting to be like, oh my God, they're perfectly related, but they're not. It's just a totally noisy estimate. All right, I will stop there because it's 12. Oh my God. Okay, bye. See you next week.
Can I use this as a way to segue